let's get into it. I'm going to basically go through the foundations a little bit more just because it would help you kind of solve any kind of problems. And also, it's kind of interesting and it might make you feel like you want to study neuroscience and physiology. So, let's get into it. Let's start by thinking that there's an imaginary cell here. It's a cell and it has the cell membrane, right, which is lipid bilayer. Right, that's cell membrane, cool. And in this imaginary world, let's say I tell you that there's only sodium, right? So only sodium, so only sodium. Okay, there's no other ions. We're only gonna think about sodium, right? Now there's more sodium outside than inside. If I ask you, would sodium want to come in? Now, if you remember diffusion, what is diffusion? It's the movement of molecules from high concentration to low concentration, right? Cool. Now, would it want to come in? Would sodium want to come inside the cell by diffusion? Yeah, it would want to come in. Yes, of course. Can it come in? Like the way it is right now? No. Why not? Because it's charged. It's charged and can't go through the lipid bilayer. All right. So how do we solve it? We're going to give it a pathway. We're going to give it some sodium channels. All right. Now it has sodium channels. Now can it come in? Probably, yeah. And they would want to come in, right? By diffusion. Cool. So sodium, oops, sorry. Sodium comes in by diffusion. All right. Cool. Now, the same thing. Sodium is coming inside. And what would happen after it's some of them have gone down, the concentration gradient? What happens when sodium is accumulating around the membrane? Because it's positive, there's going to be more positive charges around here, right? So the membrane is going to be more positive. So here, membrane becomes more positive. All right, membrane becomes more positive. And now this particular thing, like the charge of the membrane, we're at a particular time, we're just calling it membrane potential. Cool. The membrane becomes more positive. What happens when the membrane becomes more positive? So think about the movement of sodium. At first, it was going down the concentration gradient, so it was moving because of concentration. Now there's a charge element to it. That means there's more charge here, and there's more positive charge, and this is a positive ion. They would not want to come in, right? They would want to be, they would be repelled. So they would not want to come in. And that's because of the charge part of it, right? Or like just electrostatic force. And this is the concentration gradient, right? Okay. So these two forces are what's going to determine the movement of sodium. All right. So let's talk about our cell again. We have sodium coming in because there's more sodium outside than inside. Cool, but at a point, they would not want to come in because the membrane is too positive. The point where the membrane becomes too positive for sodium to not want to come in, what is the equilibrium potential? For sodium, not for everybody. Not that we're talking about everybody, we're talking about sodium right now. So sodium. All right. If we want to imagine it in like a diagram, I'm drawing a figure here of this is membrane potential. Okay, so then, oh, sorry. This is membrane potential. This is time, I guess. But the membrane potential, oh, actually, not this one, my bad. I said there has to be a point where the membrane is positive enough where sodium would not want to come in anymore, right? So sodium is not going to move. That point is plus 40. Okay. All right, and that's going to be for sodium. So it's equilibrium potential for sodium. All right, that's here, sitting here. Okay, cool. Now let's say I want to imagine a cell again, but now we don't have sodium, we have potassium, right? We have potassium. There's more potassium inside than outside. Again, doing the same thinking, two forces, concentration related force and the electrostatic force. By the concentration, by diffusion, so potassium would want to come out. Again, they obviously need some kind of channel, so this is the potassium channel. All right, so potassium would want to come out by diffusion. That's fine. The more potassium that goes out, because potassium is a positive charge, the more kind of like less positive the membrane is going to become, right? So the membrane becomes less positive, or the other way of saying is more negative, right? So the membrane becomes more negative. At one point, it's going to be negative enough that it would want to hold on to the potassium that's inside and would not want them to go out. That makes sense, right? So if they don't want them to go out, movement of potassium would cease. That particular negative potential is our equilibrium potential for potassium. That's where no movement of potassium. Cool. Now if we go back to our little chart here, if you want to like add the equilibrium potential of potassium, it's gonna sit somewhere around here, minus 90 millivolt. That's the equilibrium potential for potassium. What does it mean? What do these mean in terms of the movement across the membrane? So let's say, for example, I have a cell with only sodium in it. Sorry, let's do this one. Yeah, with only sodium in it. Okay, no potassium, just sodium. And I have the cell membrane, like the membrane potential at, I'll say minus 20 millivolt. That's where I'm holding it artificially at there. Okay, what is going to happen if I let the sodium channels open? Sodium would want to come in. The membrane's going to become more and more positive. They're going to come in. And the point where they reach plus 40, that's when they would be like, no, bro, it's kind of equilibrium potential. We don't want to come in anymore. So that's when they would stop. Makes sense, right? Same like, let's say I'm holding the membrane at, I don't know, plus 10. Again, sodium's gonna go in, hit plus 40 and stop. Let's say I'm holding the membrane at plus 50. Sodium would leave and hit plus 40 and stop. Okay, so basically, wherever you want to start, the sodium wants to move in a manner that the membrane potential becomes their equilibrium potential. So membrane potential becomes equal to the equilibrium potential of sodium, assuming there's only sodium in this universe. Okay, that's what they want. A similar thing is going to happen for potassium. I'm just going to delete this. Using, if we have a universe with only potassium, right? Then what happens? Then let's say if I, for some reason, held the membrane potential at plus 20, potassium leaves, makes the membrane more negative until it hits 90, minus 90 millivolt, and then the movement ceases. Same with, let's say, for example, I made the membrane very negative. I made it minus 110. What happens? Potassium would come in, make the membrane more positive until it becomes minus 90, and then stop moving, right? Again, the concept of saying ions want to move in a manner that the membrane potential becomes equilibrium potential. So that's their goal. Their goal is to make the membrane potential, oops, sorry about that. The membrane potential equal to equilibrium. That's our goal. Is that okay? Cool.